This lesson is an introduction to the concept of threads, which begins an explanation of Java animation, one of the things that you can do with threads. We've looked into the fundamentals of drawing still pictures in a window, but Java also contains the things you need to make the pictures move. All of the programs that we've looked at so far have been single-threaded. In fact, most programs are single-threaded because they only need to ever do one thing at a time. A windowing program is usually single-threaded because 99% of the time it has thrown up a window and is waiting for you to respond to it. Your response is in the form of a mouse click or typing some letters on the keyboard. All the time you're doing this, the program is, for all practical purposes, stopped in its tracks and doing nothing other than paying close attention to the input you're giving it. You may click on an OK button or something, instructing the program to do something, so then it throws up an hourglass cursor and completely ignores you while it runs off and does the job you requested. Once it has finished, it may or may not tell you what it did, but it comes back and waits for you to give it some more input. If something is wrong with the program, it may go off and never come back. You've had this happen, where a program just quits responding to you. The only thing you can do is kill the program. The operating system doesn't know what the program is doing, so you may get a warning about losing data or some such, but you kill it anyway, knowing that you can come back and pick up the bodies later. But it doesn't have to be this way. It's possible to have your program do a separate job in the background while it's paying attention to you. You've used a word processor or something that requested that it send something to the printer. Nothing happens at the printer for a few seconds, but control is returned to you immediately. Sometimes a window pops up asking you for printer options, but as soon as you answer the questions and click OK, the printing process is off on its own in the background. You can continue to edit or whatever as the word processor spools out the data to the printer. In this scenario, the print spooling is done by a thread. Ultimately, the printing itself may be done by a separate process, but that's another thing. What I'm talking about here is the same program doing two things at once. While the main thread is waiting on the mouse, a separate thread is off doing some special chore for you. This threading is not limited to just one background task. There can be several of them at once. A simple example would be a web server. You have your website on a server and several people address it with their web browser all at once. Each visitor to the site can get their own thread running, and each one can go their separate ways through your web pages. There are other ways of doing this, but I hope you get the idea. The whole point is that you can have your program do several things at once. Same program, different tasks. You pick the class that you want to be able to execute in a separate thread, and you implement an interface named Runnable for it. The Runnable interface requires that you have a method named Run. And it's this method that will be called by the thread. That is, when you start your thread, the thread will call this run method, and you can do anything you want to in that method. However, once your run method has finished and returns to its caller, the thread quits. So inside the run method, you must complete whatever chore the thread is supposed to do. You must create a thread object specifying an object of the class that implements the runnable interface. This has the effect of establishing the existence of a new thread, but nothing has happened yet. To start your thread running, you simply call the start method of the thread object. This causes the thread object to leap into action, split itself off into its own private thread of execution, which has nothing else to do, so it calls your run method. You could actually create any number of threads on the same runnable, but they would all call the same run method, and it would be up to you to sort out which task each one is supposed to do. It may be more convenient in a large program to create several runnable classes and then start threads on a specific class depending on the chore to be done. But I'm getting ahead of myself. Anyway, that's all there is to starting a thread. The next lesson demonstrates exactly how this works with a simple example. This lesson explains a class that runs in threads. It starts running, and its constructor is the main thread, and the constructor also spins off a separate thread. Both threads, running independently, go into infinite loops and display lines of text as output at regular intervals. This is the simple thread class, which is going to be executed as two separate threads, so it implements the runnable interface. The only requirement of a class that implements this interface is that it contain a public void run method. We'll get to the run method in just a minute, but right now let's look at some of the other things contained in the class. This is the declaration of a thread object. It's declared outside of any method, so we'll be able to address it from any method of the class. This accessibility comes in handy under certain circumstances, but we're not going to be doing anything that complicated with this first demonstration of threading. Here is the top of the constructor where the thread object is created. Any valid object could be specified as the argument to the thread constructor. The requirement is that an object of the runnable type be used as the argument to the constructor, and since the current object is a runnable object, it can be used to construct the thread. There is nothing else to do in the constructor, so the start method is called to put the thread into action. At this point, the thread named Other goes off on its own and does things in its own time. This while statement is what is known as an infinite loop. That is, once this while loop begins execution, it will continue to execute because true will always be true until the program is halted. At the top of the body of the loop, a line of text is output to the screen. Also, inside the body of the loop, a call is made to the sleep method of the thread class. Now, this is a static method, so it doesn't have to be called from any object of the class. Anybody can call it from anywhere. It's just part of the thread class for convenience. It seemed to fit better there than anywhere else. All the call does is cause this particular thread to sleep for a full second before the method returns. In this example, the sleeping simulates the program going off to do something and coming back. The value 1000 is 1 second because the delay time is specified in microseconds. The call to the sleep method must be inside a try block because if something happens to terminate the sleep early, an exception will be thrown. Placing a call to sleep outside of a try block will cause the compiler to issue an error message. But anyway, the constructor will loop forever and output a line of text once a second. This is the run method that's called by the thread. As you can see, this method also has an infinite loop. And this infinite loop also outputs a line of text identifying itself. There is also a sleep method in this loop, but in this case, the sleep pauses for 2.6 seconds between outputting lines of text. This means that the main thread will produce more than twice as many lines of output as this other thread. Compiling and running the program looks like this. You can see from the text coming out at intervals that both threads are running separately. Each one is doing its own thing in its own time. This is going to help us with animation by allowing the program to pay attention to the mouse and keyboard at the same time it's painting one frame after another of the animated action. A rudimentary form of doing this is in the next lesson. This lesson is our first look at graphics animation. It's a very simple look. All that happens is a black circle moves from left to right across the window. In fact, this animation technique is a little too simple and has a problem that we're going to have to clear up later. But the point is here to show you the fundamental structure of all animation. This is the simple animation class that's a frame used to display a simple canvas component, just as we've done a number of times before. In this case, the component being displayed is called flicker. The reason it's called that will be made apparent at the end of the lesson. This is the flicker class, which is a canvas component. These are the values of the height and width of the window and the X and Y starting position of the circle. The window is wider than it is tall, and the circle is sized to exactly fit the window vertically, and it will slowly move across the window from left to right. The diameter of the circle is the same as the height of the window. The horizontal starting position is one full width of the circle off to the left. The animation actually makes its appearance off stage to your left and slowly crosses the window and drifts off stage right. By the way, it's perfectly okay to draw graphic objects outside of the window. Java just throws it away. Lots of times it's easier just to draw images out there than try to figure out where the edges are. Java just throws it away anyway. The technical term for that is clipping, and Java has a special algorithm for taking care of it. And the guys that wrote that algorithm are better than I am at clipping, so I just let them handle it. Here is the thread declaration. I call it looper because that's what it does in the run method. By the way, I don't know if I mentioned this before, but it is worth mentioning again. The runnable interface and the thread class are both in the Java lang package. This is the same package as the string class and doesn't need to be specified on an import statement. All the members of the Java lang package are like parts of the language. The constructor of the flicker class sets the size of the canvas window, creates a thread object, and starts it running. All that's left in this program are the run method to manage the animation and the paint method to draw the pictures on the screen. All the code in the run method is inside a try block. It doesn't all have to be inside the block. The only thing that requires it is the sleep method, but I find it easier to put the whole thing in there. The purpose of the run method is to execute the code in this infinite loop. It is executed once for each frame of the animation. The sleep method is used to determine the length of time between frames. It needs to be fast enough so the frames run smoothly instead of jerky, so I chose a 33 millisecond delay. This is close to 30 frames a second. Television pictures run at 30 frames a second and they don't flicker. Movies actually run at 24 frames a second, so we could have actually lengthened the delay and run things a bit slower. But 30 frames works just fine. If you get it too fast, your graphics routine will eat up the CPU time and your whole computer will get sluggish because the other programs are being starved for CPU. Notice how the value of x is adjusted inside the if statement. Every time through the loop, x is incremented, causing the position of the circle to be 1 pixel to the right of its previous position. However, if the value of x has reached the right side of the window, that means the circle has disappeared off stage right, and we need to move it back so it'll start over. Now this method is a trick you haven't seen before. Up until now, we let Java decide when it needed to call the paint method. We can't just call the paint method directly from inside the program because we don't have the graphics object to pass to it. So we do the next best thing. We tell Java that it's time to call the paint method. A call to repaint schedules a call to paint. You could actually call repaint as many times as you want because all it does is run back in the back and shout call paint. As soon as Java has the opportunity, it calls the paint method and then forgets how many times repaint shouted at it. This paint method is a little bit different because here we have a small problem we need to solve. When this method is called to draw the circle that was drawn before is still on display. That means we have to wipe out the display before drawing the next frame. To do this, we draw a rectangle the size of the window using whatever color we would like for the background. Another way to do this would have been to set the background color in the constructor and then call the method clearRect to paint the window with that color. But the result is the same either way. As you get to know Java better, you will discover there is always more than one way to do anything. Anyway, once the entire window is set to a convenient background color, we set the current color to the color of the circle. We fill the circle at the current position specified by X and Y. Now, here's what the program looks like. And there it goes. The circle slides slowly across the window. There is one problem, but you can't see it. The way this screen is being recorded and played back for you, the flicker that's appearing is automatically being suppressed. But you should compile this program for yourself, and you'll see what I mean. The flicker will be more predominant on some systems than on others, and it'll look different on different systems, but it will always flicker. What happens is the screen occasionally is updated after it's cleared, but before the new circle is drawn. So you get momentary flashes of white peeking through the black circle. Compile the program and run it for yourself, and you'll see what I mean. The next lesson is about fixing this flicker problem. This lesson explains how to overcome flicker in an animation window. The problem comes up when the picture is partially drawn and the screen updates itself. This causes part of the animation to briefly disappear and then reappear. This happens quickly, and the image flickers. This is the Smooth Animation class, which is a modification of the previous example to remove flicker. The fundamental structure of the class is pretty much the same as the previous one. Here the declaration of an image reference is made. This image object is going to be used to make it possible to paint an entire frame of our animation into memory, and then put the whole thing into the window in a single instruction. Notice that the body of the run loop has been somewhat simplified. It's no longer used to increment the value of X to determine the new position for the animated object. This is now done elsewhere. A new method named update has been added. You see, I lied to you earlier. Well, I didn't exactly lie, I just didn't tell the whole truth. Whenever you call repaint, Java schedules a call to update, not to paint. There is a default version of update defined in the component class, and we inherit that update method here because we're extending the canvas class, which extends the component class. Anyway, the default update method doesn't do anything but make a call to the paint method. But we do a little more than that. This update method, which overrides the default update method, is inserted to do some other things before it calls the paint method. Look, all you have to do is remember that if you include an update method, it'll be called whenever you call repaint. For now, you can forget about all that stuff that goes on backstage. The first thing we do at the top of the update method is to move X to the next position, the same as we did inside the run loop in the previous program. Next, if the image reference is still null, that means we've never come through here before, and we need to get ourselves an image object. We construct an image object that is the same size as the window we're displaying. Then we extract the graphics object from the memory resident image and use that graphics object to call the paint method. At this point in the program, the entire picture that we want to put on display, background and all, has been painted onto the image object in memory. This method right here paints the entire image onto the display. You see, the graphics object that's passed to the update method is the same one that's normally passed on to the paint method. So it's the one we need to use to paint to the screen. Calling this method to paint the entire image to the screen in one fell swoop is the whole key to getting rid of flicker. This method draws the whole picture on the screen in a single action that cannot be interrupted and cause flicker. I know this is some more of that backstage magic, but believe me, it does get rid of the flicker. Look, it repaints the entire window 1 pixel at a time, right? Replacing the ones that are already there. So even if it were interrupted and restarted in the middle, it doesn't matter, because at no point will any portion of the screen peek through any other portion. It can't flicker. Here, I'll show you. There. Oh, I know. It looks just like the flickering example because the techniques used for recording this movie and showing it to you automatically removes the flicker, but don't take my word for it. Compile and run both this program and the one from the previous lesson, and you'll see one flicker and the other one doesn't. It's kind of boring maybe, but it doesn't flicker. But wait, look what happens here. If you change the size of the window, the program doesn't know about it. It keeps using the dimensions and the memory resident image that it had made to fit the other window. In the next lesson, I'll show you how to resize the window and have the animation adjust to fit it. And I'll jazz up the animation a bit too. This lesson creates a moving ball that bounces off all 4 edges of the window and recognizes the fact that the size of the window has changed and will adjust to fit the new size. The first commercial computer game consisted of a cursor that was bounced off blocks of color that you could move back and forth. The game was called Pong. This is the Pong 1 class. That's a frame that displays the window produced by a component class named Pong Canvas 1. We're going to be moving things vertically and horizontally, so we need to do a few more declarations to be able to track everything. The Boolean variable moving right is true when the ball is moving from left to right, and it's false indicating the ball is moving right to left. In the same way, the Boolean variable moving down is true when the ball is moving toward the bottom of the window, and false when the ball is moving up toward the top. Whenever the ball reaches one of the edges, its direction can be reversed by simply toggling the Boolean switch on or off. Now this rectangle object is created with the height and width being 0. This is just for convenience later on, so we can check to see whether this rectangle is the same size as the window. If it's not, and it won't be, we will create a new rectangle object that is of the correct size. This is all part of the magic we're going to do to have the animation become aware of any window size changes. There are dozens of other ways of doing this, but I like this one because I thought it up. The run method is basically the same as it was in the previous example. In fact, for animation, about the only change that ever occurs in the run method is that the length of the pause will change from time to time. We'll be doing that in the next lesson, but for now, it's still fixed at 33 milliseconds. It's here in the update method that most of the new stuff shows up. The first thing we do is check to see that the size of the actual window matches the size recorded by our internal rectangle object. The size of the actual component window is returned as a rectangle object from the getBounds method. The equals method of the rectangle class is used to compare the two rectangles. If they're not the same, and we know they won't be the same the first time through because we created a 0 by 0 rectangle to get started. If they're not the same, our internal rectangle is replaced by one that contains the actual window size. Now we're doing animation, so we'll need to do all of our drawing on a memory resident image, and we'll need a new one now, the new size of our rectangle. If the Boolean variable indicates that the motion is from left to right, then the value of x is incremented by 1. If the new position of x plus the diameter of the ball has reached beyond the right side of the window, then the variable moving right is set to false, so the direction will be reversed the next time execution comes through here, which will be the next frame. On the other hand, if the moving right Boolean variable was already set to false, this else statement will cause this statement to execute, moving the position of x 1 to the left. And if it does reach the left side of the window, moving right will be set to true to reverse the movement of the ball, so it will come back the other direction the next time through here. This code checks the Boolean variable moving down and adjusts the value of y accordingly. Just like with x, when the ball reaches either extreme, the Boolean value is toggled to reverse the direction. Finally, the paint method is called with a graphics object from the memory resident image, and the image is drawn on the window. The paint method is very simple, really. First, the entire window is filled with a cyan background color. After that, a blue ball with a black outline is drawn at the current XY position. And here it goes. It started out in the upper left-hand corner, which is point 0. Both x and y started increasing, which moved the ball down and to the right. Now this continues until the thing hits an edge, and then the direction is reversed. Whenever an edge is hit, only that direction is reversed, so the ball will continue on to hit the next wall, and one direction will be reversed again. But look at this. The window can be enlarged, and the program recognizes the change and adjusts its rectangle to fit it. If you reduce the size inside where the ball currently is, it will eventually find the rectangle and use the smaller window. Once it's inside, it will careen off the sides. Well, I guess in this case, careen is not exactly the right word. In the next lesson, we'll look at a couple of things we can do that will speed up the action. This lesson is a variable speed version of the Pong program from the previous lesson. That is, it's pretty much the same program, but this one contains some new variables that make it a simple matter to change the speed of the bouncing ball. 3 values can be adjusted in the Pong program that affect the speed. The number of milliseconds the program pauses in the run loop determines the amount of time the program waits before it moves the ball again. If the sleep number is shorter, the ball moves faster, but a short sleep time causes more CPU cycles to be used up and can bog down the system. If the sleep time is long enough, it becomes possible to see the ball jump because it's moving too slowly to fool the eye. Now this version of Pong checks to see if any arguments were specified on the command line. If there were, and there were exactly 3 of them, the 3 character strings are converted to integers and stored in these 3 variables. All 3 of them have a default value. The variable named pause is the number of milliseconds the program will sleep between frames. It defaults to 33. The variable named horizontal is the number of pixels the ball will move horizontally in each frame, and vertical is the number of pixels the ball will move vertically in each frame. The integer class has a static method that reads a character string and converts the numbers it finds into an int value. This is done inside a try block because it could be that the string it's trying to convert is something other than a number, and if so, an exception is thrown. Anyway, these 3 lines of code convert the string form of the numbers on the command line into integers so that they can be used in the program. Now this is a very simple form of command line processing. To run the program and specify the values, you must specify exactly 3 of them, and they must be in the correct order. Normally, you do some stuff here to make it a bit more flexible, but this is a demo program, so I'm trying to keep the interface code simple. If you've done much programming, you know that the biological interface is one of the most difficult to handle. Humans are very unpredictable, and data coming from them can bring constant surprises. The three values are passed to the constructor of the class. The constructor receives the values and then passes them on to the constructor of the Pong Canvas 2 class, and that's where they're needed. We had to pass them through here just to get them there. These new variables have been added and will be used in the code to set the time and motion amounts. Notice the use of the this keyword. The arguments passed to the constructor have the same name as the variables declared in the class. Inside the constructor, then, it's necessary to specify which name is being referred to. Any name declared inside a method will hide the declaration of the same name outside the method, but you can specify that you're referring to the external one by using this dot as a prefix. With these three statements, the arguments passed to the constructor are copied into the variables of the object. The keyword this still has the same meaning as it did before. It always is a reference to the current object. It's just being used in a different way this time. In this version of the program, the variable named pause is used to specify the number of milliseconds to sleep. And there's one other change to the program. Instead of using x++ to increment the value, we now use x plus equals horizontal to increment it. This sort of construction may be new to you in the middle of an expression like this. All of the assignment operators can be used inside an expression, and the value stored in the item on the left is the value that results from that sub-expression. For example, in this line of code, if the value of x is 100 and the value of horizontal is 2, the result is 102 and stored in x, and that is also the value of the sub-expression. That is, the number 102 is added to the diameter to be compared against the width. This could have been written in more than one line of code and easier to read. I usually write it that way myself, but I wanted to show you this particular construction because you will come across it from time to time. In fact, I use it some, and you may see it again in a future example. Anyway, these lines of code adjust the values of x and y. The amounts of the adjustments is determined by the values of horizontal and vertical. They move the ball to its next position. The rest of the program is just like the previous example, so let's compile it and run it. If no values are specified on the command line, the program uses the default values and runs just like it did before. But let's try some other values. This is what happens with a sleep time of 30 milliseconds and the ball moving at 10 pixels horizontally and vertically with each frame. It's certainly faster than it was. Here you can get a better idea of its motion, but let's try something asymmetric. Here the sleep time is 25 milliseconds. The ball only moves 1 pixel left and right, and each time it moves 25 pixels up and down. Compile and run this program for yourself and try some different combinations. This lesson is about two forms of branching other than the if and else structures we've been dealing with. One that's used quite a bit is a multi-way branch known as a switch and case statement, and there are places where it really comes in handy. The other special conditional expression I'm going to describe is the hook and colon, but I'm getting ahead of myself. Here's how the switch and case works. You take a variable expression of some sort and place it inside the parentheses of a switch statement, and the value of the variable will cause your program to jump to a matching case statement inside the body of the switch. In this example, if the value is 1, a jump will be made to this statement. If the value is 2, a jump will be made to this statement. If the value is something other than 1 or 2, the entire block of code inside the switch statement is just skipped. Notice the break statement. This causes the program to jump outside of the switch statement. It's very important inside a switch statement that you insert a break statement at the end of each case, because if you don't, execution will drop right through to the next case, and that may not be what you want it to do. Please, when you write a switch case statement, pay attention to where your break statements go. It's a common mistake for someone new to the language to leave out a break statement, and it can cause some strange things to happen. And always put a break statement on the last one in the list, even though it doesn't matter. It's not uncommon to come back and add a new case, and you don't want to add one and be dropping through into it. You may wonder why the language was designed to make the break statements necessary. It's for flexibility. In this example, the program is written so the values of 1 and 2 go to the same piece of code. The values of 1 and 2 have the exact same result. And the case of 1 and 2 will drop through to case 3. In this example, a value of either 1 or 2 will output 2 lines of text. A value of 3 will output 1 line of text. Now, the values of the case statements don't have to be in any particular order. They don't have to be continuous or anything else. Each case statement stands alone. The value on each case statement must be a constant, and it must be unique. The compiler sorts the whole thing out and comes up with an efficient way to branch to the right place. It will reorder things if necessary, but that's its problem, not ours. The value used in a switch statement and the value on each of the case statements can be any data type as long as it is an integer. In Java, the char data type is also an integer data type, so it'll work fine. A character surrounded by single quotes this way is a character constant. That is, it's a constant value of the data type char and can be used directly on a case statement. This list of case statements will catch any value of the letter being a lowercase vowel. If you want to detect uppercase vowels also, you'll have to list them separately. Remember, Java has 52 letters in its alphabet. The keyword default is a special case, if you'll pardon the pun. If none of the other values on the case statements match the switch statement value, this one does. The program will jump to the default if you have one in your switch case statement. It's always a good idea to put a default entry, especially if it's not possible to have a value other than the ones you've already specified. It's amazing how often an impossible value shows up. We've dealt with the if-else and the switch case structures for conditionally selecting which code is going to execute. But there is one more form of conditional execution. Some folks like it, but others say it should be banished from the language. It looks like this. The hook and the colon expression here is identical to this block of if statements. Here's how it works. If B is less than C, the value of D is assigned to A. However, if B is not less than C, the value of E is assigned to A. Now that's exactly what this if statement does. This is just sort of a shorthand. I don't know of anyone who is neutral on this thing. Folks seem to either think it's cute and concise or they hate it. I guess I fall into the first group because I use it from time to time as the mood strikes me. You won't find it used a lot. But it isn't just in Java. This same construct exists in C and C++, and arguments about it go on all the time. All I can say is, if you don't like it, you don't have to use it. I'll try to remember that you don't like it and try not to use it in any of the upcoming examples, but I'm not promising anything. This lesson demonstrates animation using an image from a file and using a switch and case statement to dynamically modify how the animation proceeds. This is the Doomed Vessel class, which is a frame class that loads and displays the Doomed Vessel Canvas class. One thing that's slightly different from the previous examples is the fact that we don't bother to store the component in a reference before adding it to the window. The new statement is used directly inside the add method. This works fine except in cases where you need to call a method of the component before adding it to the window. A state value is initialized to 0. Now this could have been done just as well in the declarations, but sometimes it just feels better to do it in the constructor. Two image objects are needed for this program. The first one is the working image that we'll use to draw animation frames, and the second holds the picture of the sailboat that will move across the window. Once again, we call on the image loader class that we developed earlier to load the image of the sailboat file and create an image object containing it. To do the actual animation, a thread is created and started running. Notice that the sleep method has a variable named pause that determines the sleep length. That's because we're going to vary it during the running of the program. Here, just like we've done before, we check for a change in size of the window and create a new image and rectangle object if the size has changed. The switch statement is based on the variable named state. In the constructor, its value was initialized to 0, so this block of code will be executed first for case 0. It sets the value of x and y, so the sailboat is positioned out of the window. It's actually off stage to your left. The pause value is set to 5,000, so the next sleep will be for a full 5 seconds, and the value of state is set to 1, so the next time through here, the next case will be executed. Now here's what's going to happen. First, the sailboat will be drawn out of sight to the left of the window. Second, the sleep method will halt the thread for a full 5 seconds. Third, the sleep method wakes up, calls repaint, which causes another call to update, which will cause the code in case 1 to be the one that executes. In this state, the boat is underway. The pause time is set to 33 milliseconds, which we've seen is a pretty fair animation time, and the location of the sailboat is shifted 1 pixel to the right. This will happen again and again, with the sailboat being drawn in each position until the value of x reaches halfway across the window. Once that happens, the state value is set to 2, so the next time through here, this code will execute. Here, the pause is set to 150, which will slow down the action some, and now it's the y value that's adjusted. The boat no longer moves horizontally, but starts moving slowly in a vertical direction, downward. This state of affairs continues until the boat is completely out of sight below the bottom of the window. At this point, the state is set to 0, and the whole process starts over again. The boat is positioned out of sight left. The sleep time is set to 5 seconds. The next state value is set to 1 to sail the doomed vessel back into treacherous waters. All the paint method does is fill the background and then draw the boat on it in the prescribed position. At first, there's nothing, as we would expect, because there is a 5-second delay. Then the boat comes out of hiding. You know, public domain images for stuff like this are hard to find, so I drew this one myself. I've already told you that I don't have any taste, but this proves now that I don't have any artistic talent either. The boat has reached the midpoint of the program and switches from state 1 to state 2, and down she goes. Once down there, we pop it back up to state 0 and encounter another 5-second wait, and here she comes again. Oh, this image, by the way, is a GIF and has some transparent pixels defined in it. That's why you can see the background colors through what is otherwise a square image. Oh, and watch this. The boat doesn't adjust to the new position of the bottom of the window because we only calculate the value of y in case 0. However, in case 2, the boat is sinking, and we continue to sink it until the bottom of the actual window is found. Now, when the boat starts over, everything has adjusted itself to the new window size because we've gone back through state 0. One way to fix this would be to reset the state to 0 every time the window changes size.